Hi everyone, and welcome back for part 2 of the Standbridge Pharmaceutical problem. It's better usually in videos, teaching videos at least, to take things in small bites, so that's what we're doing here. In part 1, we took a look at what the problem was for Standbridge Pharmaceuticals and how to formulate it, put it into Excel, and find its optimal solution. Here in part 2, as the title suggests, we're going to be learning about right-hand side ranging and shadow prices, the first part of sensitivity analysis. In part 3 of this series, we'll be looking at OFCR ranging, objective function coefficient ranging, for this same problem. And finally, we'll wrap things up in part 4 by talking about the 100% rule and how we can use it to extend the results that we find in parts 2 and 3. So let's go ahead and get started by reminding ourselves what this problem is about. You run a pharmaceutical firm, and you have a client who today needs a rush order for a wonder drug called Tachyon. That client wants 7 ounces of that chemical. In order to make it, you have a staff of 3 different people: a senior chemist, a junior chemist, and a lab tech. The senior chemist and junior chemist both work up to 8 hours of regular time. That's in these constraints down here. They can also work up to 2 hours of overtime. Their regular and overtime are the Sen Reg and Sen Over for the senior faculty, June Reg and June Over for the junior faculty. We also have some other restrictions, but right now I'm not going to focus on those. That'll be enough for us to get the idea of what's going on in this problem today. Ounce made is the total number of ounces we make of this product. It's worth $300 an ounce. Tote time is the total number of hours it takes to get the job done. And as you can see, we're losing $30 for every hour that it takes. That's the penalty imposed by our client. All right, let's move on with sensitivity analysis. To get the report, I'm going to solve this problem in Solver the way I did last time. The program's already there. But when I say solve, before closing out, I'm going to click up here on the report where it says sensitivity. That's going to create an extra tab on my spreadsheet with the sensitivity report, like this. You can see the extra tab appeared down here. And now I'm going to click and open that. Let's make it a little bigger so you can see it. You'll see there's an upper part to the report and a lower part. Today we're talking about right-hand side ranges and shadow prices, so today we'll only be using this lower report. Okay, what's it telling us? Well, a quick look over for what's going on. Each constraint number gets its own row, constraints 1 through 9. Here are the names we gave to them. It also specifies where on the spreadsheet they appear. This value column tells you the actual optimal value of each variable. These E-16 values mean 1 times 10 to the negative 16th. They're actually just round-off error. Okay? When you see a number with a large negative exponent like that, it simply corresponds to 0. And so I'll put those in, making it easier for us to discuss what's going on. The value of the coefficients here are the right-hand side. I'm sorry, these are the right-hand sides of the various constraints. And they are the numbers that were given in the original problem. For example, 8 hours of regular time for each employee, 2 hours of overtime for each employee. And by employees here, I mean chemists. The lab tech can work more hours if you want. 7 ounces of chemical being demanded of the pharmaceutical Tachyon. All right, so here are the values of the actual decision variables over here. And here are the values of the values of the left-hand sides of the constraints. And here are the values of the right-hand sides of the constraints from the optimal report. Now, the other columns that we haven't talked about yet are very important. Shadow price is a key one. Shadow price always answers this question. If the right-hand side of this constraint goes up by 1, how much does the objective go up? Or conversely, if the right-hand side of this constraint goes up by 1, how much does goes down by 1, by how much does the objective function go down? Let's play around with this for a little bit to see how it would work. For example, right now we can see that the right-hand side of the senior regular hours constraint is 8. That is, that the senior chemist is allowed to work up to 8 hours of regular time. But how about if we change that value? Let's say we changed it to 9 or changed it down to 7. How would this affect the optimal solution? Well, the first thing that we look at is to see what the shadow price is. The shadow price here is 25, and shadow price is always measured in objective function units per constraint units. In this problem, the objective function is in dollars of profit. The constraint is in hours of regular time. So that 25 is telling us that the shadow price is $25 of profit per hour of time. That is, if the senior chemist were allowed to work 1 more hour, our profit would go up $25. If the senior chemist worked 1 hour less, the profit went down by $25. we're going to see in a moment that that's approximately true, but not perfectly true, because there's something that we ignored. And that's over here. The right-hand side range has an allowable increase and allowable decrease. These refer to how much you can increase and can decrease that right-hand side. The right-hand side can be increased by 1.2, that's up to 9.2, or it can be decreased by 0.8, that's down to 7.2. Anywhere inside that range, you can trust the shadow price. Outside that range, you can't necessarily trust it. It probably changes. Let's see what this means in this particular problem. Suppose the senior chemist could work up to 9 hours during regular time. This says profit should go up by 25 bucks. Let's try that. I'm going to increase the amount of time he's allowed to work from 8 up to 9. And I'm saying profit should go up by $25. Adding 25 to 934 takes me up to 959. So if everything we said is true, when I resolve this problem, that number ought to become 959. Let's see if it does. Solver, solve the program. And sure enough, our new profit is 959. One more hour of regular time for the senior chemist made us an additional profit of 25, the shadow price. But let's try going in the other direction. I'll take it back to 8 where it was, and then cut the senior faculty's regular time down to 7 hours. If I could trust the shadow price, that means my original number, which was, what, 9? Let me find out again. I'll put it back to 8 and resolve to get back to where we were. There we were, 934. If we could trust the shadow price, reducing this 8 down to 7 hours would reduce the 934 by 25. It would go down to 909. That's what's predicted by the $25 drop. But let's see if it really happens. I'm sorry, rerunning the program. It didn't go to 909. It went to 908.33. Close, but no cigar. Why didn't it work? Because we went outside the right-hand side range. Let's go back and take a look at that. I'm restoring the program to the way it was. And then we'll take a look. Look right here. That 8 can only be decreased by 0.8 hours. For the first 0.8 hours, we're going to decrease the profit by 25 times 0.8. Beyond that point, all bets are off. Shadow price changes. So, moral of the story. If you have a right-hand side range to do, step 1, make sure your change is inside the range. If it's not, the answer is, I don't know what's going to happen. So, for example, see if you can get this. What would happen if the junior faculty could work for an additional hour during regular time? Your answer should be, I don't know. The allowable increase is only 0.75. I can tell you what happens if we add 0.75 hours of time. That is, she'll bring up our profit by 13 times 0.75. But beyond that point, I don't know. How about this? How about if the junior chemist can only work for 7 hours? Can you tell me what will happen? Sure you can. Reducing this by 1 stays inside the range. Therefore, I can trust the shadow price. 1 hour of reduction in the junior chemist's time should result in $13 of profit lost. And I'll let you verify that that's exactly what happens. By the way, we can increase the number of changes that we're making, the size of a change, to more than 1 unit. For example, look at constraint 5. Constraint 5 says that the lab tech has to work for hours less than or equal to the junior chemist time. The lab tech always has to be supervised. But suppose that weren't true. Suppose, for example, that the lab tech could work on his own for 3 hours before needing supervision. How would this change things? Well, I'm talking about increasing the right-hand side by 3 because the tech's hours are the junior chemist time plus 3 more hours. Can I increase the right-hand side by 3? The allowable increase says, yes, I can. I can increase it by up to 6. That means I can trust the shadow price, which is 1. The 1 tells you that we're supposed to make $1 more of profit for every 1 more hour that the lab tech can work on his own. So, if I'm allowing him to work 3 hours on his own, profit should go up by $3. Let's verify. I'm going to go to the tech hours and change the right-hand side to make it increase by 3. I expect the objective to go up by 3 to 937. And does it? No surprises. Yes, it does. Change it back to the original problem again. I am changing it back to the original problem each time because these are talking about what happens if I change the current problem. If I modify one thing, I might have to rerun the sensitivity report. Okay, so you get the idea of what happens when I'm changing one right-hand side at a time. Changing more than one right-hand side at a time is going to cause me problems. At least it does for now. It can be handled by something called the 100% rule, and we'll talk about that a couple of videos from now. For right-hand side ranging, there's one more thing I want to talk to you about. I guess two more things I want to talk to you about. And it has to do with what's going on with non-binding constraints. Look, for example, at this constraint here. The right-hand side is 2, but the left-hand side is 1.2. So this constraint says 1.2 less than or equal to 2. It's satisfied with some to spare. It's got slack. It's a non-binding constraint. Because of that, its shadow price is 0. The shadow price will be 0 for every constraint which is non-binding. You can see it here. You can also see it up here. All of these constraints are non-binding. All of them have 0 shadow price. Because some slack means that you didn't push the constraint to the limit. And the reason that you didn't was because there's no advantage in doing so. The other thing I'd like you to notice is these allowable increases with these plus 30s here. These are actually saying infinity. It's saying the right-hand sides of these constraints could get infinitely big without making the shadow price change. Well, the shadow price for those three constraints right now is 0, saying that an additional unit of these resources is worth nothing. So if I get more and more and more of them, they stay worthless. And that's exactly what we're seeing here. A decrease of infinity can come up with a non-binding constraint too when it's a greater than or equal to constraint. That's the most common place to see it. Here, that's not what's going on, but we do have an allowable decrease of infinity. Okay, that's all I want to say about right-hand side ranges right now. Play around with this stuff and make sure that you understand what's going on, and then come back for the next video, which is about OFCR ranging.